Okay, so we have now gone through displacement time graphs. We're going to now talk about velocity time graphs. In our previous lesson, we looked at how to convert a position or a displacement time graph and make it into a velocity time graph. Remember, when we draw a position or displacement graph, a diagonal line represents a constant velocity. So it gives you that. If the object is not moving, so you see a flat line, that equals a velocity of 0. So if you can see, that's nicely displayed here. And then the object starts moving backwards. The velocity is now negative. And then you can see with that. So let's do our analysis for a velocity time graph and look at what information is given to us. Okay, so for a velocity time graph, let's also look at the gradient and also the area underneath this trend line and see what information it tells us. So the y-axis will give you the velocity of the object. It's measured in meters per second and it'll give you a direction. So if we're going up this direction here, we're going east. If we're going this direction here, it's implying we're going west. Okay. Next part is, what does this trend line show us? So we have the rise, and we have the run, rise over run. Our rise is velocity, our run is time. Velocity over time, or so to speak, the change in velocity over time, that gives us acceleration. Remember what we mean by acceleration. The speed of the object is constantly changing, or the direction is changing. You can see we started off at time 4 here at 8 meters per second, and then at 6 seconds we get to 12 meters per second. So there's an increase in speed, there is acceleration. Okay, so there's that. The next part is, what does this area underneath this triangle tell us about the displacement? So if we have a look, to find the area of this triangle, it's half length times height. The length we're looking at is time. The height we're looking at is velocity. So time multiplied by velocity gives us displacement. Okay, so this tells us the displacement of the object. All this area that we have here would tell us the displacement of the object moving towards the east. Now, displacement is a vector, so there are scenarios where you will get the opposing direction. So let's have a look at the examples. So we have an object that can be split up into a couple of motions. We have a couple of categories. So we have the distance traveled at 15 seconds, which is this component here. Or the displacement, my apologies. And to find this displacement here, it's 15 times 15 along the lines here. And that would equal to about 225 meters east. And then we get to this part of the sort of shape that we have here. Now this one's a little bit more interesting. We can actually split it off into also other types of shapes. So let's say we're just trying to measure all the way up to 30 seconds. Okay, again, I can split this off into a rectangle. So it would be 15 times 15. And then this area here is a triangle. So the formula for a triangle, if you recall, it's half times the length, which is 15, times the height, which is also 15. So at that point, or up to this point here, okay, up to this 30-second point, we've also traveled an extra 375 or 337.5 meters towards the east. If we add the 225, then as a total, up to the 30 time mark, the total displacement would be about 562.5 meters towards the east. Okay, so that's how the breakdown works there. But as you can see, the gradient line starts to drop down. So what this implies, the object is moving backwards. Okay, so how do we factor in this line here with these charts here? Idea is very simple. If east is the positive direction, and I want to add this component here, but it's moving in the opposite direction, this would be a negative value. Okay? So let's work out the amount of area covered towards the west here. That's half times 10, that's our length there, times our height, which is 30. So in total, from the 40 to 50-second mark, we've actually traveled 150 meters to the west. Okay, so there's that. There's this little part here, so this area here, that's sort of in between, so the velocity is decreasing. Okay. What does this bit imply? Well, this is implying that the object is slowing down. So at some point, the object is speeding up, then it slows down, and then at this point here, it's moving now in the opposite direction. So to speak, it's like a ball. If you throw a ball up, it gets slower and slower to the point it reaches the peak height. And that represents this point here. And then it starts falling down again, and that represents this line down here. So clearly, if we were to look at the total displacement of the object, we would need to add the values that we have here with the value that we have here, which let's show for what it looks like. Okay, so at this point here, the object has traveled 150 meters towards the east. Okay, just because the gradient is going down doesn't mean the object has moved in the opposite direction. The only time an object is moving in the opposite direction is if the velocity becomes negative. If it's decreasing on the positive side of the chart, it just means it's slowing down. So overall, that means this 150 meters east and this 150 meters west will cancel each other out. So the total distance traveled would still be, or the total displacement traveled, correct my wording, is 562.5 meters east. That's total displacement. Okay, so let's go to some questions to further our understanding. Okay, so question 9, it says determine the velocity of the car at time t equals 6. So at this point here, what's the velocity of the car? Well, it's 30 meters per second east. We don't need to use the gradient for a velocity time graph because this gradient here would tell us the acceleration of the object, not its velocity. Question 10, calculate the change in displacement of the car. So what's that asking you to do is find the entire area, so from here all the way down here from time 0 to time 14. So if you want to split it off into a couple of sections, you can do so. So from this point here, this area covered is 20. Actually, we can use a different one. So we can draw a couple of shapes to help us find the area. So we'll go from here to this line 10 here. So to find this area of this box would be 10 times 20. We want to find this triangle here. That'd be half times 6, so from 4 to 10, times the displacement from 20 to 50, that's about 30. And then this triangle here, which is half, 10 to 14 is 4 seconds in difference, by a height of 50. So if we do all that together, we will find its displacement, and its displacement would be 390 meters east. And I'll just write the answer for this one here. Calculate its average velocity. So that's looking at the total displacement traveled. So I'll just draw this one down here. The total displacement we found just then, 390 divided by 14 seconds, that's the total trip. And that's 27.9 meters per second east. Question 12, it says, what's the average acceleration? Okay, so the average acceleration is given as the change in velocity over time. So we need to look at what our velocity was, our final velocity minus our initial velocity over time. So the time taken is still 14 seconds. Okay. The initial velocity we started off with is 20 meters per second east. At time 14, our final velocity was 0. So it's 0 minus 20. That gives us a negative value of negative 1.43 meters per second squared. Now, what does this negative imply? It means that as an average, we have accelerated in the opposite direction of where the car was going on this chart. So we can actually say it accelerated 1.43 meters per second square. Oh, we don't need the negative there. West. And that would be the average acceleration of this moving car. Okay, so the final example I just want to show you is the total displacement of this moving object. These questions, obviously not quite the same thing as what we'll go through here, but you can have a try of them afterwards. So we want to find the net displacement from time 0 seconds to 7 seconds here. We can split it off with one triangle here, one rectangle, and another triangle here. Okay, so to work it out, half times 2 times 16, that will give us the area for this triangle here. We're going to find this rectangle, which is 1, 2, 3. So 3 times the height, which is 16. That gives us the displacement here. And this side here, which would be the same as what we had over here. So half times 2 times 16. So let's look at what the overall displacement is up to 7 seconds. So the overall displacement we have is 80 meters per sec, or 80 meters north. Now let's look at this motion that we have here. So now the velocity has gone into the negative, which means we're now moving in the opposite direction. So we can work this part out. This bit would be half times 1 times 8. We're not going to worry about the negative sign here because we know it's going the opposite direction. We can just talk about it at the end. That's 2 times 8. And over here is half times 2 times 8. So let's see what we get. So the net displacement that we have here is 28 meters to the south because it's now in the opposite direction. So our net displacement, or our total displacement, is actually 52 meters north. And so that's how you go through with that. Now have a go at these questions here. Answers will be shown in 3 seconds, so you can pause here. So that's the answers given there. And so with that, that concludes our lesson recording for today. Just a couple of points I just want you to remember on is on a displacement time graph, the velocity is constant if you have a straight line gradient. If it's curving up, it's accelerating. If it's curving down, it's decelerating. And we can represent this using the equivalent velocity time graph. So if it's accelerating up like that, it means we draw a straight gradient line for acceleration on a velocity time graph. If it's moving at a constant velocity, it's a flat line. And as it decelerates, it's now a straight line back down. So hopefully that was a nice little explanation on how to analyze displacement time graphs and velocity time graphs. Anyhow, if you enjoyed, like and subscribe, and I'll see you next time.